right. You guys are ready for finals, huh? That's what I mean. Yeah, yeah. Ready for them to be over. No? No, okay. How many of you have filled out the course evaluations yet? Okay, like 5 of you. So we used to be able to give bonus points, but unfortunately they took that option away because so you might have heard this from other classes or previously, but what happened was you used to be able to say, oh, okay, student ID number this, 89 blah, 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 has filled it out. They would give us a report before grades were done. Now, we don't even get to see what percentage of the class, maybe we get to see the percentage of the class gets, has completed it, but they don't divvy it up by person. So that's way too much work for me. Now, if you write me some software code that takes all those screenshots, interprets it, and tells me which students, you'll get a lot of bonus credit. Okay, so that is an option, right? I could say, all right, I'll give everybody up to 5 bonus points, but then I'll multiply it by the percentage of how many people did it, right? So there's a thought, right? I could do that. Is that a motivating thought?
Yes.
Okay. All right. So complete your evaluations, and I'll.
So it's like completely and utterly anonymous.
Yeah. So when I wonder if I could show it to you guys. It is entirely anonymous. If you guys wanted to write in some comment, if you write your name in the comment, don't do that. Then it's no longer anonymous, right? Or if you make some joke or something that identifies you, I might know that comment is yours, but otherwise it's completely anonymous. I'm going to see if I can bring up some evaluations. Actually, I know I could. I'll show you what it looks like when I get the final evaluations.
Can't let my econ teacher find out.
Yeah, I'll show you. Have you guys ever taken a look at this? Probably not, right? Do you want to look at one of my best or one of my worst? Both? Oh, okay. Let me see. Have to try to remember. Yeah, I taught. Well, I could just go back to like the very beginning. The worst was like my second semester. I'm pretty sure. Okay, this one was good, and then. All right. Oops. Back. Okay, so you can look at this for a second while I pull up the next one. That's going to be pretty generically the probably what I would see up front. So I would see. And this is like one of the older ones. So let's see, is that right? That's feedback, hang on. Okay, so this one was like my second semester teaching. Teaching style was all over the place, never really clear. Yeah, you can see. And I was teaching 117 students in that big auditorium, and I had like no idea how to manage the class. I wasn't doing any of the lectures from PowerPoint or anything. It was a mess. So the student's not wrong here saying it was a mess. Your teaching style was extremely ineffective. Some material on the test was unclear. Make sure you know how to solve the problems before you take the test. Oh, here. Yeah. So as you can see, you could make my day, and I'd be like, okay, yeah, I got bragging rights now. Okay, so that's yeah. Some of them are kind of mean, right? Now I did tell them like, hey, I'm just starting, and I want my like ratings to go up over time, so like be brutal. But then that doesn't have anything to do with the comments. So the comments are them just being honest, right? Okay, so I mean, it's not an exact comparison. That's 3110. There's probably we'll blame it on the civil engineers that gave me the bad reviews, right? So what it looks like nowadays, and I think that report's missing some of the stuff. This one has it combined. This was from my favorite class. I took students in Nicaragua, so it was like best case scenario class for me. But you see only seven of the 12 did it, so I'll get a response rate. So that's the kind of thing you'll see, right? And I'm live streaming all of this for the world, by the way, so that's fun. Okay, so then it'll collect all the people that's saying, okay, the instructor was such and such. The system automatically generates some department average, some college average, whatever. So you'll be asked these different questions, and then it summarizes them. So this is kind of the way it shows up on the reports. And then for, so blah, 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 lots of things, all that feedback together, gives some scores. And it's like these scores that maybe somebody looks at to make sure I'm doing at least a decent job teaching, right? So that's kind of how I'm evaluated. And then at some point we can get to the comments, right? So of course they liked this one. This was a special class, my kind of favorite hot topic. And I've taught it a few times, that always helps. So you guys will be a mix of like, I was kind of unclear this time, it's first time, whatever you need to say, you're gonna say, and yeah, that's what I expect. So regardless, I'll see it, and if you put your name in that, you could see the name, right? So don't put your name in there, but otherwise, this is all I see, right? It's just a comment. Okay, next comment. So rest assured, you can say whatever you like. I will read it, and in some cases, it'll make me smile when it's like, something like that, right? Or some, Okay. All right. Was that helpful? Are you inspired now? Okay. I will give some number of bonus points to your final exam, and I'll multiply it by the response rate. Okay? I'm going to do that. I'll have to think about like what makes sense about how many. Okay. So fill out your course evaluations, and everybody will be happy. All right. So I'm planning to go through the homework, kind of typical, but any big, broad questions about the final you'd like to talk about first? Yeah.
So is like, I feel like you might have already kind of answered this, but so are like the things that we've learned since the second exam, is that going to be a larger percentage of the test?
Yeah. So my aim is that's going to be about 50% of the exam. What you'll find is a lot of that stuff even calls back also. So in some sense, it'll be like, oh yeah, we're still doing this acid-base stuff or whatever. But yeah, my intent is to be about 50% of the newest stuff, and then 50% is kind of review. So it might be like 25% exam 1, 25% exam 2, and then the remaining 50% is since exam 2. Okay? So that's kind of my target. It all bleeds together. So, what I would recommend is, as you're studying, go back and check, okay, did I really struggle with something? What was it that I didn't understand? Do I understand it now? Could I do it again today if I had to? That kind of thing. All right. Any other questions? Haven't completely finished it yet, so if you have some suggested problems, you really thought one was challenging, you can let me know. Okay. All right, so I'm going to go through this homework and stop me as we go if you have any questions. Okay, so problem 1. This time I added a few of these sort of topical questions. It made the whole thing feel a little longer, but hopefully it was maybe a little better preparation for the short answers for the exam. What kind of questions maybe I'll ask. So what does a metal's coordination number mean, and what's a typical number? This would be really the number of possible ligands that can complex on the metal. So it's kind of like bonding sites, right? That's how many ligands can coordinate around the atom. Okay, and typical would be somewhere around the 4 to 6 range. There are a few that could do 2, a few rare cases that do like 10 or 12. I think uranium or something like that. But typically they're 4 to 6 range. Probably would accept it if you went to maybe 7 or 8 even. And I guess yeah, something like that. Okay, what is a chelating agent? Again, think claw. That's sort of apparently the Greek root for chelate or something like that. So it's a claw-like ligand in that it attaches in multiple spots. So one molecule that attaches multiple spots on the metal.
I just said that I said ligands that are bidentate and multidentate. Is that good?
That's the fancy way to say it, yep. So we could say bidentate, meaning like dent. We hear that a lot for teeth, but it probably also means like sight, like each tooth is a site where you're chewing or whatever. So bidentate, or the claw, maybe this claw-like analogy is kind of like maybe a maw with teeth, right? You're biting down on the ligand in multiple spots, right? So bidentate or multidentate works just fine. So any answer like that would be fine. 3, which is typically stronger, an inner or outer sphere metal ligand complex? This should be the inner sphere that's directly bonded. So if you have some metal atom, the inner would be you have your ligand bonding directly, whereas with the outer, we have a shell of hydration layer of water that stays there. Technically, the water is truly the primary ligand or something, maybe you'll say. It's acting like that. It is complexed. But there's also a ligand hanging out there in the outer sphere that's still associating, but it's just less strong. Doesn't grip it so much. Okay, problem 4 says consider a solution with 2 dissolved constituents with an IAP of 10 to the minus 3.8 and the KSP for the corresponding solid that's formed by those two things is 10 to the minus 4.5. Do you expect to find any precipitation or any precipitated solid in the solution? So if we check those numbers, we see that the ion activity product, IAP, is larger than the solubility product. That means precipitation will be occurring. So the answer would be yes. Okay. And then if we have the same situation where the ion activity product was less than the KSP, we would say, nope, it should be all dissolved, right? That's the distinction there. Okay, now we're on to problems where we need to do some calculations, aside from a quick comparison there. So how much iron, Fe2 plus in moles per liter, could be present, so could be present in a 10 to the minus 2 moles per liter NaHCO3 solution without causing precipitation of this iron carbonate, FeCO3. The solubility product for FeCO3 is 10 to the minus 7. Okay, so here what we're going to do, it turns out this is a little more complicated because we could think to ourselves, well, shoot, we need pH to know how much carbonate's there. So what I'm going to say is it's probably a good idea to make some sort of assumption, maybe even to go look it up, because you probably could do that, or to stop and consider what we learned about the equivalence points. Okay, and I'm going to be pretty lenient about what you do to get a pH to solve this problem. I'm just going to look to make sure you got something that's kind of reasonable at least, and went from there. So I don't care too much how you did it, but we need to use this information to find a pH. Now, if you recall, we had these equivalence points, and I did skip over, and I kind of regret that now, so something I'll probably change next time I teach the course. And I didn't talk much about the diprotic systems with the endpoints. Now, we did talk a bit about the graph and what that looks like, and about some endpoints on Tuesday this week, right? So we said if our pH looks like this, we have our three species, looks something like this, where we have HCO3 minus, H2CO3, and carbonate over here. We did say that the midpoint right here turns out to be pH 8.3. Okay? Now, if we add a bunch of sodium bicarbonate, NaHCO3, we're adding this weak acid in the form of HCO3 minus. The sodium's going to come off, nothing else is going to happen. So if we thought about our equivalence point stuff, where we are adding just HA or just NaA minus, this is kind of like adding that NaA minus, shifting everything towards the A minus. In this case, I'm going to call that the HCO3 minus. Okay? So we should expect that most of it is here somewhere. Okay? And if you did go and Google this, it happens to be, or if you were to take the procedures and solve for it, it would be right around 8.3. Okay? Turns out that a little bit of it goes to H2CO3 and a little bit to CO3 minus, but it's kind of going in both directions, so we end up with about pH 8.3. So if you assume pH 7, it should actually work out pretty well. Your answer will probably be a little different. Maybe it's a lot different, we'll see. But if you had anywhere between like pH 7 and 10 range, you're probably in a pretty good spot to give the problem a chance. And like I said, I'm going to be lenient on what pH you actually use as long as you thought of some way to get it. Okay, so given that, what we want to do is compare using the IAP. So again, the definition here would be, I'm also going to, kudos to you if you didn't do this, but I've told you repeatedly, we are often going to ignore the activity unless I specifically say to not do so. So we're going to assume it's dilute enough with 10 to the minus 2. Maybe that's not true, but we're going to assume. But normally we'd write this as the activity of iron 2 plus times the activity of the carbonate. And we were given that the solubility product, so at equilibrium, that's going to be equal to the solubility product. And what we want to know is how much iron can we get to before precipitation. So if we set this equal to the KSP, that's our limit, right? Technically, maybe a hair lower than that would be like where we should be, but we can just treat that as the limit here. So we're going to set this equal to KSP to find the limit. And I'm just going to say it's, at this point, I'm going to ignore the activity, right? Okay, and that means the product of these two is going to be 10 to the minus 7. By the way, this, if you were to look this up, it doesn't matter for our problem in terms of solving it and everything, but if you were to look up this value, I actually did have a typo in my transcription from where I was sourcing this material. That's not the true KSP, but like I said, it doesn't matter for our problem. We can solve it, get a number, all that. But if you were to look that up, it's 10 to the minus 10.7 or something like that. Okay, so 10 to the minus 7 is what we're using. We also want to know, all right, how much total carbon is in solution is something we're given. So I'm going to go ahead and write that to say the total carbonate here is 10 to the minus 2 moles per liter. We talked about the pH. That would be kind of the next step if we're looking towards how to figure out iron. Well, the iron we could kind of get at by saying that should be the KSP, 10 to the minus 7, divided by the carbonate, right, at our limit. So the limit of iron is going to be limited based on how much carbonate we have. So in order to get the carbonate, that's where we want the pH. So assumed or calculated or whatever you did to get something like 8.3. If you did Google, I think it says 8.35. 8.3 was what we were using in the lecture, and I think my calculations used 8.35.
So are you approximating that it's mostly HCO3 minus because sodium would dissociate completely? Most of the concentration of sodium would essentially equal the concentration of HCO3 minus.
You could take an electroneutrality approach like that, and it would be pretty close, or that would be one way to find it. Yeah. But essentially, when we add it in one form, we expect it to bias it towards that form.
To what?
Bias it towards that form. So if we added this as Na2CO3, then it would be pushing it even more basic. If we added it as carbonic acid, it would be pushing it more acidic.
Or most of it would be carbonic acid.
Yeah.
Okay.
Does that make sense? It's just like the HAE and NAA equivalence points. We remember they had some crossing point on the graph, right? Okay, so if this is where we're going with the problem, we have some pH here. Now the trick really is just to get this carbonate into a form where it's in terms of pH and our known constants, right? So K2 and our pH. So I'm going to go ahead and rewrite this because we can, well, I'm just going to take a carbonate here. So we can solve for carbonate based on the equilibrium with bicarbonate. We could say that carbonate is going to be equal to HCO3 minus times the second constant divided by H plus. Okay, that's because of our equilibrium between carbonate and bicarbonate, right? Our equilibrium reaction would be HCO3 minus in equilibrium with H plus and CO3 2 minus. Okay, so that's K2. It's shown right here. So that would be PK2, right? Okay, so we know that, and we could look up the value for that. Turns out K2 is 10 to the negative 10.33. So now we're wanting to solve for carbonate so that we can solve for iron. Now we've got the K there, we've assumed a value of pH or found one, and then the other piece is the bicarbonate. Now, the bicarbonate here, because we know the pH, we know that almost all of the solution is in bicarbonate. So practically speaking, we could probably just go ahead and call this essentially C total. And so while there's it's going to be a tiny bit off of reality, it's not going to be enough to make a difference. It's going to be a very small decimal place. So what we can say is essentially at pH 8.3, CT is approximately all bicarbonate. That gives us a really nice way to simplify the problem and then say that the CO3 2 minus is going to be equal to 10 to the minus 2 times 10 to the minus 10.33 divided by 10 to the minus 8.35. Okay, and then we can solve for the carbonate. We do that, should be 1.05 times 10 to the minus 4 moles per liter. And then we can plug that into our equation here. And then we can find our iron concentration. So when we use that relationship, we should get iron to be 9.55 times 10 to the minus 4th moles per liter. Okay, so I use some assumptions here. You could definitely go a little more thoroughly and go to all the alpha fractions that we've talked about and put them in once you've found some pH, put them all in instead of doing this assumption that I made right here. It should get something very, very similar. Okay, how's that? Okay, kind of makes sense. All right, good. Okay, problem 6 said calculate the ion activity product of a solution prepared by completely dissolving 0.1 grams of this stannous fluoride stuff we talked about in class in 1 liter of pure water. Now, one thing you'll notice is I didn't give you any solubility product. I just said you completely dissolved it, calculate the ion activity product. Okay, so technically speaking, we might have completely dissolved it and it's supersaturated. So we're going to have to treat this one as if, like, in this moment, just here's what it is. Or we just assume it's not saturated. You weren't given that information. I'm not asking you to solve for that. I just want a solution prepared by completely dissolving it. Okay? So I wanted to keep that relatively simple. Again, we're going to ignore activity. Okay, so then it's basically we just need to find the two concentrations and calculate the IAP accordingly. So the IAP should be the zinc, the tin concentration, SN2 plus, times the fluoride concentration, but we have to square that, right? So you remember we have to, when we're doing something that had 2 here, in the stoichiometry, that would be, what that would look like is SNF2 is in equilibrium, that's a solid, would be in equilibrium with SN2 plus and 2F minus. Okay, and when we talked about, anytime we've talked about our equilibrium equations, we're always talking about products over reactants where we have AA plus BB and the products, and we wrote the K as the products, I'm just simplifying here, over A to the power of little a times B to the power of little b, right? We'll just do this. So don't forget that's how we need to do it. I think that's in our formula sheet. So if we had C and D over here, right? Okay, remember that? All good? Okay, so then we need to find these two concentrations. We need to get the molecular weight of SNF2. That turns out to be 156.71 grams per mole. We have 0.1 moles. And when we do that calculation, this guy is 6.38 times 10 to the minus 4 moles per liter. And that means the fluoride is going to be twice that, at 1.28 times 10 to the minus 3rd. Okay, so that means then the ion activity product will simply be 1.04 times 10 to the minus 9. Okay. All right. So problem 7 is a bit of a strange one. It says how much acid or base has to be added to a saturated solution of calcium carbonate to adjust the soluble calcium level to the following values if the solution is shielded from the atmosphere. So we got a closed system, we're at saturation with calcium carbonate, and we want to add acid or base such that we get our soluble calcium levels to either 10 to the minus 3 moles per liter or 10 to the minus 4 moles per liter. Okay, and part of the reason I say this is a strange one is because I went ahead and solved it, thought I did a decent job, and then I looked at the book that I was following, and they had a different solution that looked like it was simpler, but they were using a complicated equation, and I got a little uncertain because I thought they were missing something, but it's probably me that's missing something. So moral of the story is, I'm not going to give you this one on the exam, first of all, and I'm probably going to be pretty lenient on how I grade it. Okay, so that's what you want to. That's what I want you to know. Now I'll show you the thought process, and I'll show you the book's answer, and we're just going to leave it at that. Okay. I think the thought process might still be helpful because it's like, okay, how are we thinking about these problems? What would it take to shift? But I just didn't quite get everything together to give you a better answer than this. Okay, so the way I approached it, I said, we've got this KSP, that's 3.3 times 10 to the minus 9. We can set that equal to our calcium carbonate species, like so. And if we're at equilibrium, then our IAP is equal to that. So when we start with a saturated solution, that means saturation, it's not supersaturated, it's not undersaturated, we're at the equilibrium. Okay, so at saturation is at equilibrium. That means the IAP is also equal to 3.3 times 10 to the minus 9. That means we can, we're not told anything about any other sources of calcium or of carbonate, and we are told it's sealed from the atmosphere, so presumably there's nothing else here. So I think we could say, if we're interested in knowing calcium or, we'll do this. We'll say that at least the initial calcium is going to be equal to the initial carbonate. And that means that we could take calcium squared equals 3.3 times 10 to the minus 9. So therefore we can get, we can solve for really both of these initial and say that's going to be 5.74 times 10 to the minus 5th. Moles per liter. Okay, so that's where I was starting. That's what I was thinking would be a good starting spot. And then we could say, all right, well, do we need to add acid or base? And how much do we need to add in order to get it to here? Now, I don't know much about the pH of the solution, but if you recall, we looked at a couple diagrams for this material, and we showed that in a closed system, we kind of had this plot that looked something like this, where we had the solid over here. And that would be, I think this was a plot of the calcium against pH, if I'm not mistaken. So I was thinking, well, probably if we're in equilibrium with some amount, my guess is that we're somewhere around here. Now, maybe I could look at this graph and calculate it myself, I'm not sure, but I just kind of made an assumption that, well, we're going to be somewhere in the middle where bicarbonate is dominating, kind of like that other one. So that if we add 1 unit of acid or 1 unit of base, we are going to be taking away or adding 1 unit of carbonate. Because if we add any acid, it's changing one proton will change 1 CO3 2- to 1 HCO3-. And that takes away 1 carbonate every time that it actually happens, which that's our titration. And when we are in the correct area of our plot, that's happening 1-to-1. And this slope here would be a 1-to-1 slope. And then it becomes a 2-to-1 slope. So I was thinking to myself, well, we could compare the 10 to the minus 3 to the 5.74 times 10 to the minus 5th. And if our initial calcium is that low, we want more calcium in solution, then essentially that would mean we need to add base so that, or no, let's see, that would be, maybe I drew my graph wrong. I'm trying to remember. If we added base, that would mean we have more carbonate, which mean we could have less calcium. But here we want it, so we would need to add acid. Oh yeah, I wrote that wrong. I did write it. Okay, so we need to add some amount of acid to allow our calcium to go up, right? So we need to shift left on this plot. So I was thinking to myself, we could simply take the net strong acid could be equal to this 5.74 calcium initial times 10 to the minus 5th, bless you, minus the 10 to the minus 3rd. Wait, nope, sorry, what am I doing? Where did I get that number? Hang on. I have a different number for my CO3 initial, and I'm trying to figure out where that came from.
What I did, I basically did the same method too, but I did KSP over 10 to the negative 3. So it was like 7 KSP equal to the calcium carbonate, and then dividing it by that to get your original of the other one.
Yeah, and I think I wrote it up here. Let's see. I have 2 different numbers written for my initial carbonate. And did you get 3.3 times 10 to the minus 6 for that? Or?
Yes. Okay.
Because I have that here, which is what I was going to write here. Yeah. So I've done something wrong that's confused me even further with my notes. So I'm just gonna skip ahead basically and say, okay, this is what I did. Do you have something? Maybe you see what's going on?
No insight. I just wanted to know why the initial calcium was squared. There's no coefficient.
Because I was substituting into here. I was just saying if the initial CO3 is equal to the initial calcium, those two are equal, so I'm just going to square one of them. But clearly that's not even what I did to get this number, so... But I was using so I got this number, I think, from CO3 2- with this guy over calcium, but yeah, this is recursive and bad and not the right way to do it. But we're going to set that aside a moment and just say I got an answer. So I'm going to write that answer. And I apologize, I thought I had a better handle on this for you. But I will say that the book, we'll use a different color here. The true correct answer was just to find some shortcut to say that you needed 10 to the minus third moles per liter of the acid. Or it's actually equivalents per liter, sorry, would be the right way to say it. Okay, now, like I said, they were using an equation. Essentially, they used the electroneutrality equation and did some hand waving and didn't explain anything. So I was like, well, I've got an answer that I think works. I'm now second guessing that, sorry. So the answer to both was just the amount it had to shift, apparently. That feels a little wrong to me because it feels like we did need to account for the initial starting point, but
Wouldn't we use that as the endpoint and then find the difference from the others?
I think this probably comes down to relating the net strong base equation to essentially the carbonate on the right side. So, and then the fact that you can relate the calcium to how much carbonate's in there. So I did not teach this well enough for any of us to figure it out. But you can imagine that if you remember our equation for alkalinity, we have CO3 in that equation. We have HCO3 minus, CO3 minus. And if we had calcium in our net strong base set up here, we could also write the carbonate in terms of calcium on the right side. So they're doing something fancy like that. I didn't teach you that. My bad on this question. But apparently there's a kind of a quick and easy trick to do that. So I don't think I'm going to be counting against you on this problem. Fair enough? Okay. All right. So moving on then. 8, I was asking you to balance a few redox reactions. First, iron 2 plus oxidized by oxygen to iron 3 plus. So we'll go ahead and do the iron side of it. We're going to start with the most oxidized species on the left per convention, going to the most reduced, like so. And this one is pretty simple. We just need to add an electron, right? That'll balance out the charges. We don't have to worry about any hydrogens or oxygens or anything in that one, water. So that's the first one. And then we need to do our second half reaction, which would be oxygen. And essentially we are going from O2 is the more oxidized version compared to, because that's 0 valent, compared to water, which is going to be 2 minus. We're going to need 2 oxygens, so we'll go ahead and balance that there. That means we need 4 protons on the left, which means to get a neutral, we need 4 electrons here. And to combine them, that means we need to multiply this guy by 4. So essentially we're doing 4 atoms of iron for every 1 molecule of oxygen, which makes sense because O2 is essentially giving up 4 electrons to go to 2 waters. So we just have to, and we're only doing 1 electron transfer in the iron. So once we balance that all out, we should have 4 Fe 2 plus an oxygen plus 4 protons is going to 4 Fe 3 plus and 2 waters. Okay, good on that? Yeah.
Is it considered wrong to write the first half reaction like flipped, like Fe2 plus goes to Fe3 plus?
I wouldn't say wrong, just not. I think the convention is to keep the most oxidized one on the left, but as long as you're getting the right answer, you're doing the process correct. And like I said in the past, if something does get confusing like that, as long as you're sure that the electrons end up balancing and you combine them in a way that they balance, you should get the right answer. Okay, so next up we've got ammonia, NH4 plus, oxidized to NO3 minus by bacteria using oxygen. Sometimes for these guys, I do like to pause a moment to calculate the oxidation states here. So for the nitrate, if we stop and think about it, we've got, it has to be +5 oxidation state because each oxygen is going to be 2. And so that would be a 6 total, -6 total, and the net is a -1, so we need a +5 to balance it there. Likewise, for the protons, we've got 4 pluses, and the net is a 3 plus, so the nitrogen here has to be a -3. So before I even get going, it kind of gives me some guidance, like for every one of these I'm changing, that's 8 electrons I need to swap. That's something I can double check with later as I balance. Okay, so we're going to start then. That also tells me which one's more oxidized, right? In case it wasn't already obvious, the one holding a bunch of oxygen happens to be the most oxidized, right? So that's going to be nitrate on the left, NO3 minus, plus whatever we need, in equilibrium with the NH4 plus here. Okay, so we're going to need 3 waters on the right to balance the oxygen there. Then now we have 10 hydrogens on the right, so now we need 10 on the left. And currently we have a +1 charge on the right and a +9 charge on the left. So we need to go from a +9 down to a +1, so we need 8 electrons. Okay, so that's where we get the 8 electrons. That matches what we were expecting, so that's good. The water equation is going to be exactly the same as above, O2 plus 4H plus 4E minus in equilibrium with 2 waters. Okay, so then when we combine these, we're going to have to essentially take this guy, which gives us 4 electrons, and multiply it by 2 so that we can get the 8 electrons canceling 8 electrons. Our final balance then will be NH4 plus 2 oxygens in equilibrium with nitrate, 2 hydrogens, 2H plus, and a water. Okay, and we have, excuse me, that should have been 2H plus. So now if we check, we have a +1 charge on the left, +1 charge on the right, and I think everything else should be balancing here. Okay. All right, next up was one that I assigned and then realized it was a little trickier, so I did make this update. Hopefully you saw that in the file. So we're oxidizing metallic silver, solid silver, to this Ag2S, so a silver sulfide, by H2S. And I make the little note that says this is a special case. Instead of adding H plus to balance protons, use H2, hydrogen gas, and recognize that it's the hydrogen undergoing the redox reaction, not sulfur. So we've got something strange happening here. And if we look at the oxidation states, it might make a little more sense. So silver, of course, as a solid, it's in 0. And then when we have it as Ag2S, well, S likes to be in a -2 state, a lot like oxygen. And so that means we have 2 times the +1 states for the silver. +1 is the other state that silver likes to be in. And if we have Ag2S and we compare that to H2S, what we'll find is that H2S is also a -2 and 2 +1s. So the sulfur is not actually changing oxidation state. That's the key here. So the sulfur is not one of the half reactions, although it looked like it should be. I'm going to be quite lenient on this one too, because I think you probably could balance it, but we really didn't talk about these exception cases in class. All right, so to do the silver first, we'll start with the, the oxidized side should be on the left, right? So this should be Ag2S. On the left with the silver solid on the right. To balance this, really, let's balance the sulfur itself. And what I'm going to do is you could potentially balance it with an S2-, or you could go ahead and balance it with H2S. Doesn't actually matter either way. We're going to end up with the same charge electron situation. I think the most obvious way to do it would be to leave it as H2S. Therefore, you have to add 2 hydrogens over here, which kind of is a little contradictory to, I guess, the instructions I gave you in a sense. The instructions really were for the next part. So maybe I shouldn't have said that. I don't know. Like I said, I'm going to be very lenient. That would be the first half. The second half is really where I was trying to give you the help and to say that to take protons to H2 gas, we're going to need 2 of them. And this is going to be the second half reaction, is going from the oxidized H+ to the reduced H2 gas. And to do that, we'll need 2 electrons. Right? So with that, we can balance these 2 half reactions. They both have 2 electrons, so we're good there. And the fully balanced system should look like this. Okay. Does that make some sense? All right. Good. So problem 9, here was a lookup table, kind of like a Gibbs free energy type of problem where we wanted to use the electrical potential E0 and PE0 values, comparing a few different half reactions, trying to get some information about, okay, what is the what's the energy potential to go from one reaction to the other. Okay, so the first thing I did was I took a look at the reactions themselves and the listed E and PE values for each, for the oxidation of each one of these guys. And so I was looking at them in reference to being oxidized to Cl-, or reduced maybe, their reaction to Cl-, and then comparing the two. Okay, so that was my target as a way to get the differences. So you'll see in the book, for example, or excuse me, in the appendix we would have the reaction ClO3- plus 6H plus 6E- is in equilibrium with chloride and 3 waters. And we'd get values for each of these, right? So I'm going to list them as the ClO3-, we had E0 and PE0. These were 1.446 volts and 24.50. Now I could also look at the ClO2 minus. That one had a reaction where, and actually I'm gonna flip this, because essentially if I add these two together, we can see the conversion of ClO3 minus to ClO2 minus. Okay, so you'll see that come out when we balance this properly. So I'm going to invert this one, but I'm also going to give the values that the book lists here. The values were 1.609 volts and 27.27. Okay, so on this, in this case, if we do Cl minus plus 2 waters, that'll be in equilibrium with the ClO2 minus, 4 protons and 4 electrons. Okay, so if we add these together, we get a weird number because electrons are not matching. So what we can do is multiply this guy by 3 and the other guy by 2. And then they will match and balance, and we'll get a combination where we're essentially converting ClO3 minus to ClO2 minus. So that reduction. So that means if we take these values over here and accordingly multiply them by 2 and by 3, add them together, we'll get our answer, or subtract one from the other rather. So we could say that for the change, for the exchange, the E should be negative 1.935 volts, so not favorable. And this guy should be negative 32.81. Okay. This is coming from like E cell is equal to E1 plus E2, sort of a deal. In this case, I flipped one, so I subtracted them. Okay, does that make sense? All right on that? Okay. So we're going to do the same for the next problem. It's kind of writing out a little bit more. I already have one of them written out, so this time I'm just going to add the ClO2 plus 4H plus 5 E minus in equilibrium with Cl minus and 2 waters. Okay, I ended up flipping that one and multiplying it by 4 in order to balance it with the ClO3 minus, and I had to flip that one, multiply that one by 5. Okay, when I combined those, flipped and combined, then I ended up with, well, let me go ahead and say E naught for this specific half reaction was 1.1495. Excuse me, 1.495. And the PE naught was 25.33. And when I combined them, I got a value here of 1.25, bless you, 1.25 volts and the PE naught at 21.18. Okay. Good on that. All right. Problem C said determine which half reaction, A or B, will occur when ClO3 minus is used to oxidize Fe2 plus to Fe3 plus at pH 7 if all species except H plus are at unit activity. So when we're at pH 7 and we're at unit activity, that's just meaning we're at standard state. So we can use the E standards, right? So what we can say then is our E naught for a cell is simply the E naught for the first plus E naught for the second. Okay, and we have a new half reaction for Fe3 plus an electron going to Fe2 plus. And for this one, our E naught was 769, and PE naught was 13.03. Okay, so we can calculate using the values we've found in A and B, we can combine those reactions with this half reaction to get the E cell here. So for the case in A, essentially what I was looking at was negative 1.935 plus 0.769. That's going to give us a value of negative 1.166 volts. And for the B reaction, we would have 1.25 plus 0.769 gives us 2.019 volts. Okay, and that would be the more favorable one since it's positive.
So I kind of said that because I got a more positive value for the I kind of like stopped at just the reduction potential from the tables, and so the one that had the more positive reduction potential, I just put that instead there.
Yeah, the only trouble with the tables is that the table was giving you a half reaction that wasn't the full deal, because this says, well, maybe for part C, maybe it's fine. Well, actually no, because this is saying when ClO3 minus is used, and A and B were both using ClO3 minus, and so it's really asking what's the end point, right? Is it ClO2 or is it ClO2 minus? Yeah.
I have a quick question for that B real quick. Is that supposed to be times 6 instead because of the electrons in the ClO3 minus?
Down here. Mm-hmm. Let me write out what I.
Instead of 4. I don't mean the I think the times 5 is right, but is the 4 supposed to be 6?
Let's see. So for the ClO3, we had 6 electrons. Yeah, I think you're right, because for some reason I was probably thinking that was a 4.
The ClO2
yeah.
is 4. Or no, the O2 minus is 4. So that's probably...
Yeah, so I think I did that wrong. Now I think, okay, so you're saying this should be a times 6?
No, that one should be 5, and then the 4 should be a 6.
There we go. Okay. Do you have the numbers? Did you do these?
Not correctly.
Okay. So I'm going to double check these then on my own time. because I did that wrong here. Okay. That means it's a little questionable about which one this happens, but because that puts into question this answer here. I expect it's probably B because I think it's going to end up more positive, but we'll have to see there. But the process makes some sense here. Okay.
Should we expect this on the final?
I think if I put one of these questions, I'm going to probably try to make it a little more straightforward. I didn't feel like I did a great job mapping this out during class. Okay, I've got just a bit more time, so I'm going to move along here. So problem 10 gives us a water containing 1 times 10 to the minus 4 moles per liter of CO2, having an alkalinity of 2.5 times 10 to the 4th equivalents per liter, has a pH of 6.7, and the pH is to be raised to 8.3 with sodium hydroxide, strong base. Answer the following questions. So part A says how many moles of sodium hydroxide per liter of water are needed for this pH adjustment, and the pKs are given. Now this one is really just testing to see if you remembered that special number of pH 8.3. We described that as kind of the titration endpoint for bicarbonate. So when we are under that, every time we add base, we are shifting from a carbonic acid to a bicarbonate. And up until we reach pH 8.3, that's pretty much 1-to-1. We could also add an acid coming from a more basic condition and be converting carbonate to bicarbonate on a kind of a 1-to-1 ratio. So it turns out this is a very simple question, and all we really have to say is that our H2CO3 total is approximately equal to our C total at the start. Well, actually, it's not even, we don't even have a C total. We're given that it's equal to 1 times 10 to the minus 4th moles per liter. And so if we are going to add enough base to convert all of that, or effectively all of that, minus some very small decimal place, to bicarbonate, then we just need to add that amount of base. So that is also our answer. So and just as an explanation, we are going to the bicarbonate endpoint.
Also, that's when the amount of strong base added is equal to the acid added, and it should go over to the pH of its conjugate base, since the base is being added.
This is very much like going to that NAA endpoint. Okay. So each OH minus we add essentially converts 1 H2CO3 to HCO3 minus. Okay, so that's the logic. Therefore, when the next problem, part B, says how many moles of lime, so calcium hydroxide, would be required, well, every 1 calcium hydroxide we add, we get 2 of the hydroxides, and therefore we need half the amount. So this is just simply going to be the amount of CaOH2 should be 5 times 10 to the minus 5th moles per liter. Okay, so that problem was a lot faster than maybe it felt like it was going to be, right? Yeah. I mean, you saw the reviews I got, right? I do put red herrings out there sometimes. I'm gonna do my best to like not overly complicate things for you. So I will try not to. Okay. All right. Good on that? Sounds like if there were issues, you're probably just trying to complicate it a little bit, trying to make use of the alkalinity. Okay. Last problem here, and this I think this is a good classic one that if I didn't teach you how to do this semester, then I've done my job wrong. And so it's probably bad that I saved it for the very last problem and didn't really talk about it too directly till very recently. But having said that, hopefully you'll be able to see this, even though I have like 8 minutes to solve it, I think you'll get a good feel for it, and maybe I'll even put it on the exam in some form or another. So we have a question that says, what is the pH of pure water in equilibrium with 1 atmosphere of carbon dioxide at 25 Celsius? So there's a couple things you have to look up to get this going. I gave you the pressure of CO2. Now, of course, our atmosphere is a very small portion of carbon dioxide. This problem has a very large amount of carbon dioxide in it. At 1 atmosphere, that's as if everything we were breathing was carbon dioxide. That's not the situation for natural rainwater, for example, which is something like maybe the more typical form of this problem. So we can solve for our dissolved carbon dioxide by simply saying this should be that pressure times Henry's law. The Henry's law constant we need to look up or find somewhere. This turns out to be 3.1 times 10 to the minus 2 moles per liter per atmosphere. It's important that we get it in those units, so then we can take these two together. Since we have 1 atmosphere of it, that makes this calculation pretty simple. That means we have 3.1 times 10 to the minus 2 moles per liter of dissolved carbon dioxide in this system. Okay, and that's constant, doesn't change with pH because it's open with the atmosphere. Now, to solve the problem, to find a pH, I'm going to go ahead and build an electroneutrality equation. Okay? So in pure water, we should have cations on the left, H+. There should not be any other cation in solution, right? So we can put that on the left, OH- on the right, and then we have a couple of anions to deal with. We have bicarbonate, the -1 charge, and then we have to do 2 times carbonate because it has a 2- charge. Now, what do we know if we add a bunch of H2CO3? What's that going to do to the pH?
The pH should lower and the bicarbonate concentration should be negligible.
So the pH will lower, and at least the carbonate should be pretty negligible, right? So I'm gonna say we have an acidic solution approximation. So it's acidic solution approximation, and say that because of that, we're going to treat the most basic species as 0. That will simplify it, and then we are kind of in business here with something that maybe we can solve for H+. If you recall, we can put water, so OH- in the form of H+, if we know the K water is 10 to the minus 14. So we can get this into H+ form. What's that?
You can't cancel out the OH-.
It might become trivial, but it's better to keep it. Yeah, so if we look at it, there's a good chance it is trivial in the end. So maybe you could, but I'm just going to keep it. And we're going to take a look at what happens. Okay, so we have H plus equal to 10 to the minus 14 divided by H plus. And the bicarbonate we can also put in reference to H plus because we know that we have the bicarbonate in equilibrium with the carbonic acid. So to find our HCO3 minus, the bicarbonate, based on the equilibrium reaction here, we can rearrange the equilibrium reaction. We do need to know K1. That's another thing maybe you need to look up. 10 to the minus 6.35 is typical at room temperature. So K1 there, so HCO3 minus, we can say this should be equal to the K1 times H2CO3 dissolved divided by the H plus. So when we put this in here, I'm going to go ahead and write this as 10 to the minus 6.35 times 10 to the minus 2, excuse me, 3.1 times 10 to the minus 2, because we actually know that value. Divide that by H plus. And if we want to solve this equation for H plus, well, let's just multiply everything by H plus and simplify it, right? So then we get H plus squared on the left equal to 10 to the minus 14th, and now we can kind of debate whether or not that's relevant here, plus 10 to the negative 6.35 times 3.1 times 10 to the minus 2. So 10 to the minus 14 probably is irrelevant, but I left it in there, and I got an H plus concentration of 1.18 times 10 to the minus 4 moles per liter, which would give us a pH of 3.93. Okay. Does that make some sense? Do you guys think to use electroneutrality? No? Okay. Got to tie in those other pieces, right? Okay. So I'm strongly thinking about putting this one on your exam or something like it. Probably not 1 atmosphere, but something like that. So make sure that that feels okay. All right. We will see you on Monday.